Okay, so we are interested in limits because we need to take the limit of different quotients, the limit of rise over run, to find derivatives that will help us understand slopes for nonlinear functions. That's how we got here. And this is going to be a very brief treatment of a pretty big subject of limits. I want to go through the definition of limits and then talk about some rules. And I'll say right at the outset, the definition that we're going to get to is on the hairy side. I think a lot of the reason why people think calculus is hard is because the kind of definition that limits are an example of is hard to parse. And for our purposes, it's okay if you feel like you're not getting that. I even really thought about, should I even put that in Math Camp or not? And I don't want to make it sound harder than it is either. So I am putting it in. And getting better at understanding limits will help you, especially if you want to take advanced methods courses. The idea of limits will come up in ways other than calculating derivatives. So you guys can learn it, and it is worth learning. Most people kind of go through this iteration of, you try to wrap your brain around it, maybe do some applied problems, go back to it. It makes a little bit more sense. It pops into focus for a while. It pops out of focus. And so let's start that process now. But what I want to say, especially if calculus is new to you, you don't need to feel super comfortable with that definition to continue. And by the time we get to the rules of limits, they are really nice and straightforward. All right, so with that introduction, let's just sort of remind ourselves of what the idea of a limit is. So the limits we were interested in were those limits of difference quotients. So the limit as delta x gets as close as possible to 0, what we claim is that rise over run, those slopes of secant lines, get as close as possible to the slope of the tangent line. That is the claim, okay? The distance we're going on the x-axis gets smaller and smaller. The slopes of those lines that are connecting 2 points on a function are getting closer and closer to the slope of the line that just touches the function at a single point. Okay? The slopes of the secant lines that are connecting 2 points on the function, those are your difference quotients, your rise over runs. The slope of the tangent line is the slope of that line that just touches the function at one point, and that's what we've decided is going to be our analog of the slope for a nonlinear function. Okay. So the overall idea of a limit, I'm going to write the limit slightly differently here. The limit as any variable x approaches some value x0 of any expression involving x, f of x equals k. The idea is as x gets as close as you want, arbitrarily close, that's what we like to say. As x gets arbitrarily close to x0, f of x gets arbitrarily close to k. Okay, that sounds okay. So let's try to write that out precisely here. Okay, so here's our definition. And what I'm going to do is I will write it out and talk through it, and then also to go back and talk about some of the parts of it. Okay, so the definition, when we say that the limit as x goes to x0 of x equals k, that means that for all epsilon greater than 0, that's a lowercase Greek letter epsilon there exists some delta, lowercase delta there, and that is also greater than 0, such that, put a comma there, the absolute value of f of x minus k is less than epsilon whenever the absolute value of x minus x0 is less than delta. Okay, like I said, it's a lot, that definition. So I want to say 3 things to sort of help us wrap our brain around that. Okay, so first of all, I want to point out that those absolute values, the absolute value of the difference between f of x and k and x and x0, all they're doing is they're telling us we're talking about distance here. So when we say that absolute value of f of x minus k is less than epsilon, didn't need to make that mark there, I wanted to just highlight it. This is less than epsilon. What we're saying is the distance between f of x and k is less than epsilon. Okay, so k is within, sometimes we'll say, an epsilon neighborhood of f of x. Okay, and same here, this absolute value is also just indicating distance. Okay, so whenever x0 is no farther from x than delta. So these are both just telling us about distance here. Another thing that's helpful in kind of picking apart this definition, and indeed even just the thing we're defining here, is to kind of do the thing of, okay, what are the parameters, what are the variables here? And for limits, x0, k, and even the function itself, f, are parameters, okay? We're writing them in a general form now because they can take lots and lots of different values, but in a specific context, they would have specific values, okay? So, for example, if we had a limit as x goes to 1 of 1 minus x squared over 1 minus x, we're going to assert that that equals 2. We're actually going to show this in a couple of minutes. What we've got here is the 1 is my x0. This is the value x is approaching. Okay. 2 is my k. This is the value of the limit. And this is my specific f of x. Okay, so specific function here. So really, the only thing that's really a variable here is x. X is the thing that is moving. It's getting as close as possible to 1 in this context, x0 in the more general one. Okay, so this is the kind of the real variable here. Okay, one other thing I want to say about this definition, let's see if I can copy it to the next page here. Okay, that didn't copy so well. Let's, I know what let's do. Let's add a better page there. That's got the right thing. Okay, it's still awfully big, but I think we can work with that. Here we go. Great. All right. So here's that definition, and I've already noted that the absolute values here are just telling us about distance, and that it's sort of helpful to remember that in a specific context, we'd have a particular x0 in mind, a particular function, and a particular value for the limit. The other way to think about this definition is to think about it as a kind of conversation, and kind of a conversation that involves a claim and a challenge to that claim and a rebuttal, if you want to think about it. Okay, so claim is going to be that k is the limit of f of x as x approaches x naught. Okay, and so let's again sort of think about what we really mean here. What we're saying, the claim is that f of x is as close as you want to k when x is close enough to x0. If I'm saying that k is the limit of f of x as x is approaching x0, this is my claim. Okay, so I'm starting that. The challenge, so you, skeptical you say, okay, you said, Kathy Bond said, as close as I want. How close do I want? I'll tell you, epsilon. Epsilon is as close as you want. So you're giving me a number epsilon, and you're saying, okay, f of x better be no farther than epsilon away from that k whenever x is close enough to x0. Okay, so you're giving me a number, and the idea here is that epsilon is small, right? If epsilon is big, it's not that much of a challenge. So you give me a really, really teeny number, and my rebuttal here is, you give me epsilon, okay, I'll tell you delta is close enough. Okay, whenever x is within delta of my limiting value here, yes, your epsilon is going to be satisfied. You tell me how close you want the function to be to k. I tell you how close x needs to be to the limiting value so that all of the x's that are closer to the limiting value than the one I picked, for all of those x's, f of x is within epsilon of k. Okay. So again, the way to think of it as a conversation is there's this claim that involves one thing being close enough to another thing, or as close as you want to another thing. You tell me how close you want, and I'll tell you how close you want the f of x to be to k, and I tell you how close x needs to be to x0 in order for not just x, but all the x's in between x and x0 to have functional values that are less than epsilon away from k. Okay. So the conversation frame tends to help a little bit. I'm not going to say that that it makes a hard thing easy. It's still, I think, a hard definition to wrap your brain around. The idea of limits are there. There's a level of abstraction here that we haven't encountered in any of the math that we've done so far. And as I say, it's worth thinking about, trying to expand your ability to imagine things like this and to pick apart complicated definitions like this, but it is not, strictly speaking, necessary for the stuff that we're going to be continuing with. Okay, so it's fine to just look at this for a while. When you're tired out, put it on the back burner and go on to the next thing, which are the rules of limits. And for as hard as the definition is, the rules of limits are really nice and straightforward. That we didn't care about. Rules of limits. Let's get control of the iPad here, back to a reasonable color for rules. These are going to look like rules of logs, rules of algebra. They have that kind of flavor. These are ways that we can calculate limits by finding them for part of a complicated expression and building up an answer. So the first rule is that the limit as x goes to x0 of k is k. The limit of a constant is a constant. Okay? The limit as x goes to x0 of 3 is 3. This might seem like kind of a dumb thing. Why do you need to take the limit of a constant? And the answer is just the point I made before, that this is helpful if you're taking the limit of expression that's got a lot of parts to it. Now we've got some rules that really look like algebraic rules. Okay, so the limit x goes to x0 of f of x plus g of x is the limit x goes to x0 of f of x plus the limit x goes to x0 of g of x. Okay, so the limit of the sum is the sum of the limits. Same for multiplication. The limit as x goes to x0 of f of x times g of x equals the limit as x goes to x0 of f of x times the limit as x goes to x0 of g of x. Okay, I'm going to need to add a qualification to both of these. So I'm going to put some asterisks here just to remind myself to go back over that. The limit as x goes to x0 of f of x divided by g of x. The limit of a quotient is the quotient of the limits. Everything really nice here. Like I said, these rules, nothing tricky about them. And then rule 5, the limit as x goes to infinity of 1 over x is 0. Okay. So those are 5 rules that can get us off the ground and take quite a few limits of more complicated expressions with them. Okay, these asterisks. We had 2 asterisks on rule 2 and rule 3, and I'm actually going to put 3 asterisks on rule 4. So making a little space over on the side of my screen here for the 2 asterisk point, as long as the limit of f of x, again, x going to x0, and limit g of x, x goes to x0 exist. Okay, if those limits don't exist, then we're not adding them up there. And the triple star on rule 4, same deal, as long as f of x and limit of g of x exist. So same as for rule 2 and rule 3, but we also need the limit of g of x not to equal 0. So no surprise here, you can't have a 0 in the denominator. And let me just be careful here and add x goes to x0 in all these cases, x goes to x0. Okay, so some comments and an example. First comment on this business of what does it mean for limits to exist. Next page there. That means that the limit is some number. Okay, and it's like, okay, fine, limits are numbers. What would not count as existing is if the function is heading out toward infinity. So people will sometimes write things. I'm not going to write it because I don't want you to write it. People will write things like the limit as x goes to x0 of f of x is infinity. You shouldn't really do that. Infinity is not a number, okay? It's not something that we can do algebra with. It creates confusion, okay? So when I say the limits exist, it means that they have to be some finite number. Okay, here's an element of the set of real numbers. And again, this is qualifying what this means here. So for these rules about the limit of a sum or the limit of a product or the limit of a quotient, you can use those as long as the limits are like numbers, okay? If they are going off to infinity or negative infinity, it means the limit doesn't exist and you can't do algebra. So that's the limit of the rules of limits, so to speak. That was comment number 1 here. Comment number 2, another sort of point about infinity. Rules 1 through 4. So all my rules except rule 5 apply to x goes to infinity as well as x goes toward x naught. Okay, so comment 1 is a case where you have to make a big distinction between limiting values that are finite numbers or the direction of infinity. So for k, it's an important difference. But for x0, if you, instead of having a finite number here that x is approaching here, 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 if you have infinity, that's fine. The rules all apply. Now, of course, it's important that the limiting value be the same on both sides of the equal sign. If you have the limit as x goes to x0 on one side, that's not going to tell you anything about the limit as x goes to infinity. Okay. The final comment is going to be kind of a segue into a quick example I want to do. I guess it's going to be a comment on cases in Rule 4. The comment is that g of x, the limit of g of x goes to 0, often equals 0 at exactly the point we're interested in. Okay, when that is true, try to simplify. So let me just show this in an example, and that'll be the very last thing in this video. So let's look at that example that I included in passing. Okay, the limit as x approaches 1 of, what did I have? 1 minus x squared over 1 minus x. Okay, this is exactly what I'm talking about here. The limit as x goes to 1 of that denominator equals 0. So it looks like we can't use Rule 4. And this is super annoying because probably the reason why we're interested in the limit is exactly because the function's not defined there, and it's not defined because the denominator is 0. So it's kind of like we've got these rules, and in the case where we're most interested in using them, it seems like they don't help. But there's this great trick here. The trick is, as long as x does not equal 1, it can get as close as you want. It can get so close, no, even closer than that. But as long as it's not exactly equal to 1, then look what we can do. Then I'm going to factor the numerator there. That's the difference of perfect squares, right? It's 1 plus x times 1 minus x over 1 minus x. And as long as x is not exactly equal to that point where this function is undefined, and 1 plus x is, these are the same. Okay, so I can do this cancellation every place except where x equals 1. And when I'm taking the limit, I'm interested in how x is behaving when it's really close to 1, but not when it's there. So I can do this, okay? So what this means is the limit as x is approaching 1 of the thing I started with, 1 minus x squared, 1 minus x, equals the limit as x goes to 1 of the other thing. That's the limit I can take. Okay, the limit as x goes to 1 of 1 is 1. The limit as x goes to 1 is also 1. It's kind of tautological there, and it is indeed 2. So that is kind of cute, right? That same trick we're going to use when we apply the rules of limits to difference quotients to find derivatives. And that's what we're going to do in the very next video.